Hey everyone, so this is an extension of the rest of the lesson that we ran out of at the end of the period today, so I apologize for that. Had a lot to talk about and still getting used to having only 60 minutes to plan a 75-minute lesson. So I'm going to start you guys back a little bit earlier here because I skipped over this with the time. Originally I was going to have you and Desmos do this, so maybe pause the video real quick and try this. What I wanted you to do is to draw me 3 quick sketches. And instead, if the points were 2, 1, and then 3, 4, 5, 6, 2, 3, instead it was 6, 3, can you sketch 3 possible graphs of f? Remember that the function must be continuous and differentiable when you're doing this, all right? So pause the video and just do that for me real quickly. All right, so welcome back. At this point, hopefully you will have unpaused and you are ready to go here. I'm just quickly drawing couple sketches here. So back when we did the first one on Desmos in class, I had you draw all of these, right? So what ended up happening is because the average rate of change here was 0, right? You could connect the 2 endpoints and make a straight line. And when you connect those 2 endpoints, you're always getting a straight line. You're always getting a horizontal tangent line, or sorry, a horizontal secant line. Let me be more clear with my pronunciation here. So because you're getting that horizontal secant line, we're guaranteeing that the instantaneous slope is here. So based on the fact that the mean value theorem was what I said it was earlier in class today using that easy pass example, Rolle's theorem is essentially just a specific example to the mean value theorem. Rolle's theorem talks about specifically when the endpoints are equal, but if the endpoints aren't equal, think of this as Rolle's theorem but tilted. So if I draw this graph, right? Or if I draw this graph, or if I draw this graph. What we're seeing in all of these examples is the average rate of change is this green dotted line, and the tangent line is going to be this red line, and notice that there's a guarantee of at least one time where the tangent line and the secant line are going to be parallel to each other, aka they're the same. Here it is again. Guarantee that when this is your secant line, this is your tangent line, that the secant line and a tangent line are parallel. So there is a guarantee that there will be one parallel tangent line to the secant line. Now there could be 2. In this first example, there happens to be 2. In this example in the middle, there's only 1, and that's the only guarantee the mean value theorem is going to give us. In the case of the linear function, of course, there are an infinite number of these tangent lines because the line itself is tangent, being a linear function. So this is a more of a visual perspective of what's happening here. In class, we obviously use this example here about the easy pass, all right? That the easy pass can track your average rate of change, your average speed. And if your average speed exceeds the speed limit, it's a guarantee, because they can't track your individual speed, all right? They can with a radar gun, but the Easy Pass doesn't have that. They can do average speed, and if your average speed is above the speed limit, they can guarantee only that speed. They can guarantee at some point you were instantaneously going the average speed. You have to have. So that's the reasoning why, in my example here, we were speeding. Here's a more mathy example. Given the continuous function x cubed, what is the slope between 1, 1 and 4, 64? Well, the slope's going to be 64 minus 1 over 4 minus 1, or 63 divided by 3. So my average rate of change here, or my average slope of the secant, is 21. So it's saying, if possible, find a point in the interval from 1 to 4 that has the same slope as your answer above. And again, the slope at a single point is our derivative. So we would want to take the derivative of this, and we get 3x squared. And here's the thing. So here's your x cubed graph, right? This is what it visually looks like. And what we're trying to say is, at some point between 1 and 4, the slope has to be 21. So if we do that, we're going to set that 21 equal to 3x squared. And when I solve this, we're going to get x is equal to plus or minus the square root of 7. Now, because we're only looking in the interval from positive 1 to positive 4, the value that is going to satisfy this instantaneous equals the average is actually just going to be single-handedly x equals square root of 7. So this is the value that satisfies the mean value theorem. Okay, so with that being said, we're going to do a couple examples, and this is where I'm going to have you pause to try, and then I'm going to go over the example once we're done. So pause this video and go ahead and try this example out now. This is the second example that we didn't get to in class. All right, so welcome back. So first thing we need to do with the mean value theorem is verify that the hypothesis is true. So f of x is continuous, and the reason why is because x equals 0 is not on the interval. Look, we're only looking between the numbers 1/2 and 2. So because 0 is not on that closed interval, we can indeed say that f of x is continuous. F of x is differentiable because when you take the derivative, we get -2 over x squared, and the only point that is going to create a situation where the derivative is not continuous is x equals 0, which once again, for the same argument, is not on the interval. Therefore, we can apply the mean value theorem. We can apply the fact that the instantaneous rate of change will equal the average rate of change. Here's my instantaneous rate of change. Here's my average rate of change. So all I'm going to have to do now is to verify the mean value theorem and find these values that are satisfied with it is I'm going to set these two things equal to each other. And so when we solve this, we're going to get -2 equals -2x squared. That's 1 equals x squared. X is equal to plus or minus 1. Now the question specifically says, find the values of c. So find the x values on the interval in between the points that satisfy. So the only value that we are going to verify here, so I'm actually not going to have that answer circled, is we're just going to write x equals 1, or you could say c equals 1 if you want to be more particular with the way that they're saying it here. You're only guaranteeing this value because -1's not on the interval. Last example for you on this video is going to be this one here with a square root. Go ahead and try this out and unpause when you're ready. Okay, welcome back. So this example is the most important example of this video because this is going to establish the conditions of mean value theorem right to the extreme. The function square root of x minus 3 is only continuous from values 3 or higher, including the number 3. You can plug 3 in and get the square root of 0, which is a viable number. So this function f of x is continuous on the closed endpoint 3 all the way to infinity. Therefore, on the closed interval from 3 to 7, f of x is indeed going to be continuous. So we get a check mark here. Is f of x going to be differentiable? Well, when you take the derivative, you get 1 over 2 square root of x minus 3. So once again, any value less than 3 is going to be a problem because you have a negative square root. But the number x equals 3 would give me a 0 slope in the denominator. Therefore, it is a vertical tangent line. It's a vertical slope. But keep in mind that the mean value theorem says it has to be continuous on the closed interval and differentiable on the open, meaning as long as I can take derivatives between 3 and 7, I'm fine. And because it's differentiable from 3 onward, we can indeed say that it's going to be differentiable. So this is a yes and a yes, even though it's really close to being not. If it was 2.99, right, it'd be no now, all right? So with that being said, MVT can be applied. So here's my work in blue that is going to verify that. So we set the average rate of change here as 1/2. So there it is. There's my instantaneous rate of change, aka my derivative. And from here, all we're doing is solve to guarantee the value that it's going to be, which in this case is going to be x equals 4. X equals 4 is our final answer here. So that'll conclude the extra examples. Based on this, hopefully you should be able to complete the textbook problems now with a little bit more ease than before. And good luck with that, and let me know if you have any questions.